Okay, I have a physics problem here. It's a very interesting problem. It's two sentences long. When you first read it, it seems like it's going to be really easy. And then when you start working on it, you start to hit a couple of dead ends and feels like they didn't give enough information. But if we're careful, we'll get through it with some lots of algebra, very few numbers, and just have to be careful, slow, and methodical. So let's read the problem carefully first. It says, at half of maximum height, the speed of a projectile is 3/4 its initial speed. What was its launch angle? Okay, so first of all, let's do a vector that represents the speed. Alright, so there's my vector. And the initial speed is going to be v naught. So if they had given us a number, we would see that number right there, right? We would have, if it was 20 meters per second, we would have 20 meters per second right here. And, but they didn't do that, obviously, but we're gonna separate our vector into components here. So we all know that we do that by making a triangle. Alright, and the angle that our launch angle that they're asking for would be theta. It would be right here, right? Okay, and then the horizontal component, if they gave us a number, we would do v naught cosine theta would go right here. In all of our problems, we would call this v naught x or something like that. We'd have v naught x, x and v naught y. Alright, and we would put v naught x right here and v naught y. Alright, and from our days in trig, we know that v naught x is going to be v naught times the cosine of theta. And our vertical component, make these into vectors so that, alright, our vertical component would be v naught sine theta. Alright, and if, so I'm going to do something right now that's going to be handy later. It's really not necessary for solving this problem, but if they had given us these components instead of giving us the velocity vector, if they gave us these components, then we would say that v naught equals the square root of v naught x quantity squared plus v naught y quantity squared. Alright, and we all know this as the good old Pythagorean theorem, right? A squared plus b squared equals c squared, and since we want to know what c is, or in this case v naught, we take the square root of both sides, so we have that. Alright, now let's substitute these in here. So if we do a substitution, we're going to have v naught equals square root of, for v naught x, we're going to substitute v naught cosine theta. So let me put some parentheses, v naught cosine theta, and the v naught x is squared, right? So we're going to have squared, and then we're going to substitute for v naught y. V naught y is here, v naught sine theta, and that's squared also. Alright, now since these are multiplied, I can distribute the exponent. And that's going to give us v naught, v naught squared, that's a 2 right there, v naught squared cosine squared theta plus v naught squared sine squared theta. Okay, so again, I'm just doing this. This isn't really going to solve the problem, but this is something we're going to do later with some other numbers that we're going to generate from some equations. And I just want to go through it one time, so when we do it the second time, you're familiar with it. You know what I'm doing. All right, let's factor. We have a v naught squared here and a v naught squared here. So let's factor those out, and I've got v naught squared times cosine squared theta plus sine squared theta. Sorry, my 2 looks a little bit like a 3 right there. Okay. So now from trig, we all remember that cosine squared plus sine squared is just 1, right? So now we've got v naught squared times 1. Alright, and before I determined that this was going to be a 1, in fact, let me just go ahead and write it again. I know this is a little tedious, but I like to do things step by step so everybody sees what's happening. Alright, so v naught squared, the square root of v naught squared, that comes outside and it's just going to be v naught, right? So I have v naught, and as we said, this becomes 1. So I have v naught times the square root of 1. Well, the square root of 1 is just 1. So v naught equals v naught. Okay, so seems a little silly, but we're going to use this same train of thought later and to solve this problem. Okay, now if you want to copy this down, I would say pause the video and you can get this copied down, because I'm going to start a fresh sheet here in a second. Alright, so let me get this out of the way. So just real quick before I take this away, the problem says that at half of maximum height, this whole situation occurs. So in the interest of breaking things down and doing it a step at a time, for us to know what half of maximum height is, first we have to find maximum height. So let's do that. We're going to find maximum height. Alright. And we have an equation that probably everyone is familiar with. Oh. Alright, I'm sorry for jumping around here a little bit. Let me go back to this real quick before we get too far. Alright. Here's our velocity vector, and this is a projectile. So the projectile has some motion that looks like a parabola. Imagine throwing a baseball or something like that. It goes up, travels to whoever you're throwing it to, comes back down. So throughout this whole thing, our horizontal velocity is going to stay the same, right? Because our acceleration in the horizontal direction is 0. And 0 acceleration means the speed stays constant. So our horizontal speed is going to stay the same. What's going to change is our vertical speed. Our vertical component is going to get smaller and smaller, or slower and slower as this projectile gets closer and closer to its maximum height. So that's what we're working with here. Most of the work we're going to do on this problem is going to be with the vertical velocity because the horizontal velocity never changes. Okay, now we're going to find maximum height. So there's an equation that helps us to find max height, and it doesn't involve time, which is good because the original question didn't say anything about time. So here's the equation we're going to use. It's V final squared Alright, so a lot of you are probably used to seeing this with a plus sign here. Gravity is just a number, 9.8, but since gravity points down, we're putting a negative sign, and V final here is just the final velocity at whatever height we give. So it's not necessarily the final velocity at the very end of the problem, it's just the velocity at whatever height we give. In other words, it's not the initial velocity, it's the velocity at the end being when the projectile has traveled to this height, or distance, vertical distance in this case. And so since it is vertical distance in this case, I'm going to call this V final y and V initial y. Alright, so a couple things here. We said that we were going to look for maximum height. So we know that maximum height occurs when the final velocity is 0, right? When any projectile reaches its maximum height, its vertical velocity is 0. So for max height, our vertical velocity is going to be 0. So that's going to be a 0. And don't forget the substitution we did for initial vertical velocity was just V naught sine theta. Okay, so the reason I'm saying V naught sine theta is because it puts V naught y in terms of just V naught. So essentially cuts down on the number of variables we have, and which is what we did here. Instead of having V naught x and V naught y, which is two different variables, I have V naught and V naught. Now at the same time I introduced the angle, which is another variable, but we need that angle in there because the equation said, or the question said, what was its launch angle? Alright, bear with me here, we're going to get through this. So this is 0. And this is going to be V naught sine theta squared minus 2 times gravity times d. Alright, so we're going to manipulate this around until we have d equals something, and whatever it equals, that's going to be our D max. And again, I can distribute this exponent. So I'm going to have 0 equals V naught squared sine squared theta minus 2GD. Alright, so I'm going to add 2GD to both sides. So I get 2GD equals V naught squared sine squared theta. Alright, so again, we're still looking for D. So I'm going to divide both sides by 2G, and then I'll have the D by itself. So D equals V naught squared sine squared theta over 2G. Alright, now that D is, I don't have enough room here. I'm going to write it over here. I'm going to call it D max, right? Because since we called the final velocity 0, we know that that's going to occur at maximum height. So this particular D is D max. All right. Now the problem said at half of its maximum height, and we have maximum height. Now, if this were a normal problem where they gave us a bunch of numbers and we were able to do all the math and we ended up with a number here instead of variables, let's say that we found out our maximum height was 10 meters. Well, we would just multiply that 10 times 1/2 and it would be 5 meters. And so the 5 meters would be half of our maximum height, right? But unfortunately, we don't have a number here, so I can't just take whatever the max height is and multiply times 1/2 and get another number. So I can't get a final number for half maximum height. However, I can do what I said, and you'll see what I mean here in a second. So D max is V naught squared sine squared theta all over 2G. Alright, so why did I write it again? Well, here's the reason I wrote it again. If D max equals this, then half of D max equals half of this. So I didn't do anything crazy or wild here. This is just our old rule from algebra, right? Whatever I do to one side, I got to do to the other side. So if I have an equation for D max and I want to know what half of D max is, well, I got to take D max and multiply times a half. And whatever I do to one side, I got to do to the other side. So now this quantity right here is half of D max. Now, what am I going to do with that? Well, I'll tell you. I'm going to take this and substitute it back into this original equation, and I'm going to substitute it in place of D. Now remember, this D only became D max because we made the velocity be 0. But if I put half the height in for D, and then work on, actually I need to put it in this equation where I've already made this substitution. If I put it in there, then I'm going to find my new final velocity at half height. So let me just do this so you'll see what I'm talking about. Alright, first I'm going to write down this equation, but instead of a 0 here, I'm going to put V final y squared. Alright. Alright, so I'm going to have v final y squared equals v squared initial sine squared theta minus 2gd. Okay, so now if I put this here so we can reference it. If I put in a distance, then I can find the velocity at that distance. Alright? Well, my distance is half maximum height, which is here. So the distance I'm going to put in is v naught squared sine squared theta over 2g times 1/2. Alright, so let me write this equation with this substituted in for d. Alright, so we're going to have v final y squared equals v initial, or v naught squared sine squared theta minus 2g times d. Well, here's d. Oop, can't forget the squared over 2g times 1/2. Okay, so let me get this out of the way. So now we see that some things cancel here, right? I got a 2 on the top, and I have a g on the bottom, and a g on the top. Oh, and this 2 on the bottom, so I canceled the 2 and the 2, and the g and the g. And so now v final y squared equals v initial squared sine squared theta, and then this minus sign goes here, and I'm going to write the 1/2 out front, so 1/2 v naught squared sine squared theta. Alright, we're getting close, hang in there. So now I can manipulate this a little bit, and I'll see that I think the best thing to do is to factor out a v naught squared, and well, actually I don't even have to do that. Here I have 1 times v naught squared sine squared theta minus 1/2 v naught squared sine squared theta. So 1 minus 1/2 is 1/2 v naught squared sine squared theta. Alright, so I didn't do anything, if you didn't follow that, it's no different than if I had, x minus 1/2 x. Well, x minus 1/2 x would just be 1/2 x. So, same idea here. It's just algebra. Alright, so here is my final y velocity, or vertical velocity, at half height. This is it. So, you remember this that I did before. This was my initial velocity, or the hypotenuse of my velocity vector, and so I'm going to do this same thing for V final. This is V initial. I'm going to do V final. Well, what's V final going to equal? V final is going to equal the square root. And we said that the x component was never going to change, right? So that goes right in there. V naught cosine, let's see, V naught squared cosine squared theta plus, and I need the final vertical velocity here, and I need it to be squared, okay? So V final y, alright, and it's squared because my final velocity vector is just going to be another vector, V final, and I'm going to have the x component, which we said would be the same as this, which is V naught cosine theta, and then the vertical component is going to be V final y, and when we do our Pythagorean theorem, we would square this, add them together, and take the square root. So that's what we're doing here. We have squared this, it's here, and then we're going to take this, square it, we add them together, take the square root, we get V final. Okay? So now, if I look back up here, right here I have V final y squared. Well, I have an equation here that tells me that V final y squared just equals this. So I'm going to substitute that in to here. Alright, so plus this, I'm going to make this substitution. So it's going to be 1/2 V naught squared sine squared theta. Alright, and just a little side note here, the parentheses really aren't necessary, but I'm just trying to make it clear what I'm doing. Okay, so I'm going to make 2 more substitutions on this before we continue, and actually let me do one more step. So V final equals square root. Alright, I'm going to factor a V naught squared out of both terms. Alright, so this is going to be V naught squared times cosine squared theta plus 1/2 sine squared theta. Alright, probably something like 5 more minutes. We'll be done with this. Alright, I'm going to make one more. I'm going to look back at the original problem. It says that the speed of it, at half its maximum height, the speed of a projectile, alright, the speed at half its maximum height is this one, is V final. And so it's saying that V final, that's what this is, V final of a projectile is 3/4 its initial speed, V naught. So what that is saying is that V final is 3/4 V naught. So I have V final here, and so I'm going to do this substitution. So in place of V final, I can put 3/4 V naught. So right here I'm going to have 3/4 V naught. Okay. Now I'm going to have, I have the square root of V naught squared. So I'm going to pull that out. The square root of V naught squared is just V naught. Alright, and I'm trying to combine some steps here. One more substitution that I'm going to make. We all remember from trig that 1 equals cosine squared theta plus sine squared theta. Alright, so let's solve for cosine squared theta. I'm going to do that by subtracting sine squared from both sides. So I'm going to have 1 minus sine squared theta equals cosine squared theta. So this equals cosine squared theta. So I have cosine squared theta right here, so I'm just going to substitute this in for it. So in place of, so this came outside, so it's no longer in there. And now I have this cosine squared theta, which I'm going to substitute this. So I'm going to have 1 minus sine squared theta plus 1/2 sine squared theta. Alright. Now, I can divide both sides by V naught. And so I'm going to divide this side by V naught. V naught divided by V naught is 1. So I'm left with a 3/4. Same thing over here. V naught divided by V naught is 1. So that goes away. I'm going to have 1 times this square root. And 1 times anything is just that thing. So we don't need to do that. Okay, here I have negative sine squared theta plus 1/2 sine squared theta. And that's going to give me 1 minus 1/2 sine squared theta. Okay. Next step. Let's square both sides. If we square both sides, we get rid of the square root symbol there. So square the left side, I get 3 times 3 is 9. 4 times 4 is 16. And over here, the square root sign just goes away. So I've got 1 minus 1/2 sine squared theta. Okay. So now I'm going to subtract 1 from both sides. So if I subtract 1 over here, 1 minus 1 is 0, so that goes away. And 9/16 minus 1, I need a common denominator. So 1 with a denominator of 16 is just going to be 16 over 16. Alright, so 9 minus 16 is going to be negative 7 over 16. Alright, and if I'm going to multiply both sides by a negative 1/2, so I'm sorry, I'm going to multiply both sides by a negative 2, not a negative 1/2. Sorry, I said that. I'm going to multiply both sides by negative 2. So if I do negative 1/2 times negative 2, that becomes a 1, positive 1. So I'm left with sine squared theta. And over here, I'm going to have Negative 2 times 7 over 16. Negative 2 is the same as negative 2 over 1 times negative 7 over 16. 2 goes into 2 one time. 2 goes into 16 8 times. The negatives cancel. So I'm left with 7 over 8 equals sine squared theta. Alright, so now I'm going to take the square root of both sides, and that's going to give me square root 7 over 8. And usually we would write a plus or minus right here, but I just want I want a positive angle, so I'm going to use positive 7 over 8. And square root of sine squared is just going to give me sine theta. Alright, and we know that to find theta, we have to take the inverse sine of both sides. And inverse sine of sine, they cancel each other out, and we're left with theta. So, what we have to do is punch this in our calculator. And yes, I have my ancient calculator here. So, here's how it works on my calculator. I'm going to have 7, enter that. And I'm going to have 8, enter that. So this is 7 divided by 8. I'm going to divide. And then that's square root. I'm going to do the square root. And then I'm going to do inverse sine. On my calculator, it's called arc sine, or it's labeled A sine right there. So orange key, A sine, and so we get theta equals 69.295. So that's it. Really long video, but I went slow, so make sure everyone follows the steps that I did so you learn how to do the problem instead of just getting the correct answer. Thanks. Leave some comments below. If there's anything that you didn't understand, let me know. And that's it. Just a really big, long algebra problem.